Welcome back to Chapter 2, Section 6. In this section, we're going to be looking at the graphs of rational functions. Now, these are very similar to polynomials in the type of math that we have to do. We will just be looking for some slightly different things here and there. Um, but but the actual math involved is basically the same. We're still going to be factoring polynomials and stuff like that. The nice thing is that generally speaking, uh, the ones that are in rational functions tend to be a little bit easier than some of the ones that we've been dealing with as straight polynomials. Our learning targets: find the domain and range, find the domain of a rational function. Graph rational functions using transformations. Hey, transformations, they're the same as they always have been. Evaluate limits based on graphs and or equations. And then find asymptotes, intercepts, and graphs of rational functions. So the first thing is what is a rational function? A rational function is the quotient of two polynomials. So we just have one polynomial divided by the other polynomial. As long as that denominator does not equal 0. We'll talk about that in a minute, but basically that gives us a vertical asymptote. So like an example of a rational function could be something like r of x. It could be f of x. It's just r of x for rational function because we're using f of x for the numerator. But we could have like r of x equals x squared minus 3x plus 2 over x squared minus 9. That's a rational function. Now, one of the things we do is we have to find the domain. Now, generally speaking, the domain is going to be a restriction on the domain. The domain is all real numbers except for what makes the denominator 0, because it can't be 0. Again, those vertical asymptotes. So if we had x squared minus 9 equals 0, that means that x squared would equal 9, which means that x would equal plus or minus 3, which means for the domain, x can't equal plus or minus 3. So all we need to do for the domain is figure out what makes the denominator equal to 0, and then x can't equal that. So that's the general idea of what a rational function is. How would we deal with these and transformations? For that, we would start with the reciprocal function, which is a specific rational function. The reciprocal function is just 1 over x. The graph of it looks like this. It's the hyperbola. We have asymptotes on both axes because neither of our variables can equal 0. And then we can use transformations here. The transformations are exactly the same. If we wanted to stretch it by 2, like vertically, g of x would just be we multiply by 2, so we'd get 2 over x. If we wanted to do a translation, let's say we wanted to move it to the right 3, so we have 1 over x minus 3, and then up 2, plus 2. I know that this does not look like something like that, but it actually is. To write it in that form, we would need to make a common denominator. So we have x minus 3 as the denominator, so 2 would be 2 times x minus 3 over x minus 3. So this g of x, we have 1 plus 2x minus 6 is going to be 2x minus 5 over x minus 3. These two g of x's are the same. It's just the top one, we're looking at it as a translation, which is fine, but it does make a rational function because we can write it as a polynomial over a polynomial. So how do we graph these things? When we're graphing them, we need to look at a few different things. We need to look at the end behavior, asymptote. The end behavior is what's happening when x is getting really, really small, going down to negative infinity, and when x is getting really, really big, going up to positive infinity. For that, we look at the degrees. If the degree of the top is bigger than the degree of the bottom, there is no horizontal asymptote. We get what's called a slant asymptote, um, which I'll explain that in just a second. If the degree of the top is less than the degree of the bottom, the asymptote goes to 0 because the bottom is getting bigger faster and faster and faster, and so it is dividing by bigger and bigger numbers very, very quickly, and thus going to 0. If the two degrees are the same, then it's just the ratio of those leading coefficients. So it's the coefficient of the first divided by the coefficient of the second. So that's what's happening with the end behavior. Vertical asymptotes are where the denominator equals 0. It's where the domain doesn't exist. So in that last one, we found that the domain is x doesn't equal plus or minus 3. The vertical asymptotes are x equals plus and minus 3. So it's the same thing as the domain, it's just an equal to instead of a not equal to. The x-intercepts are what makes the numerator 0. So we have to see what makes the numerator 0. That gives us the x-intercepts, because that's how we make a fraction equal to 0. And the y-intercept is just if we plug in 0 for x, because it's when x equals 0. So you get rid of all the x's and what's left. And that's if it's defined. So let's take a look at one or maybe a couple of these. So here, the first thing we want to look at is end behavior. We have f of x equals x cubed over x squared minus 9. So the end behavior, we look at the degrees. We have a cubed on top and a squared on the bottom. The cubed is bigger, which means there's no horizontal asymptote, but there's a slant asymptote. When that degree is bigger, what we can do is we can actually just look at those first ones and simplify. Because as x is going to infinity, this minus 9 isn't going to do anything. And so, I mean, it gets less and less and less. So basically, when x goes to infinity, we're looking at x cubed over x squared, which is y equals x. That's our slant asymptote. As x is getting really, really big, we're going to have this asymptote. It's going to look like y equals x. So if we take this graph, when we get it graphed, and we zoom it out really far, it's going to look like the line y equals x with some funky jazz in the middle. So that's the end. That's our end behavior there. The vertical asymptotes happen when the denominator equals 0. So x squared minus 9 equals 0. We already saw this. We can add the 9, x squared equals 3, so we get x equals plus or minus 3. So we have 1, 2, 3, 1, 2, 3. We're going to get our vertical asymptotes here. Then we need some zeros in our graph, because zeros are some important points. The zeros are when the top equals 0. So x cubed equals 0. Well, x cubed equals 0 when x equals 0. So we have the point, this point. That's the only 0 that it's going to have. And then the y-intercept. Well, if we plug in 0, we get 0 over negative 9. So the y-intercept equals 0, which being that the 0 is at 0, we have the point 0 comma 0, so that's both. So it's going to cross there. Now we just need to figure out where it's going to be in the graph. Is it positive? Is it negative? What's going to happen? We know that we have an asymptote here, and so it's going to either be going down to negative infinity or up to positive infinity. We also have the asymptote here, so it's going to be coming that direction. It's going to be coming in from this way. Now the question is it going to go up to positive infinity or down to negative infinity? The answer here is it's going to go down to negative infinity. Why would it go down instead of up. How did I know that? In order for it to go up to positive infinity, what has to be in between here and this asymptote? At some point there, it would have to cross 0. It would need a 0. There is no 0 out there, which means it's either going to be all positive or all negative. Since we knew it was negative, it's going to stay negative. The same basic principle will apply for the plus side, because we know it's going to be coming that way, and then it has to go up instead of down, because again, there's no 0 over here, so it cannot cross that axis to get to an asymptote down there. Now in the middle, it's going to cross 0, and on either side it will either be positive or negative. So we need to figure out, is it going to look like this? Is it going to look like this? Is it going to be one of these guys in the middle? And for that, like, those are the only 4 options right now in the middle, because it's going to hit the 0 and it's going to have an asymptote on either side. So it's either going to be positive or negative for each one of them. For that, we just need to see, is the graph positive or negative? So if we plugged in a value in between the 0 and the asymptote, let's say plug in 1, we want to see it, and -1, we'll see if we get a positive or a negative value. So if we plug in -1, we're going to have -1 cubed over -1 squared minus 9. -1 cubed is -1, and then over -1 squared is positive minus 9. It's going to be -1 over 8, -8, which is a positive value. So when x equals -1, it's going to be positive, which means we're going to have one of those 2 options, because it's going to be coming up to this positive asymptote. And how about when x equals +1? We'd have 1 cubed over 1 squared minus 9. That's 1 over -8, which is a negative number, which means all the y values here are going to be negative, which takes it down to that lower asymptote. So this is how we can graph rational functions. We can do the same thing going backwards. If you're looking at a graph, where are the zeros? That'll give you some factors for the numerator. Where are the vertical asymptotes? That gives you factors for the denominator. And then from there, everything else generally falls into place. You might need a negative in there, or something like that. But generally speaking, once you have the factors for the numerator and the denominator, it's just little tweaks and fine tuning to get the rest of it. So this was a quick deal for rational functions. We'll actually see more of them in the next section. But until then, keep working problems, keep asking questions, and as always, happy mathing.